Good morning, everyone, and thank you for joining the fourth webinar in this series of EU-SysFlex webinars. My name is Hans-Peter Höschle from Vito Energyville in Belgium, and I am the work package leader of work package 3 within the EU-SysFlex project. In today's second webinar from work package 3, we continue presenting results, this time from task 3.4. For those who've missed the previous webinars, the webinars are available on YouTube and they can also be found via the project website. As said, we present the results of task 3.4 entitled Impact Analysis of Market and Regulatory Options, Advanced Power System and Market Modeling Studies. Throughout the presentation, you will have the possibility to ask questions using the Q&A dialog at the bottom of your screen. We will collect all questions and address them after the presentation of the speakers during a consecutive Q&A session. If we cannot answer the question, we will come back to you via email. Let us start with the webinar and let me quickly show what you can expect from the next 1.5 hours. I will start by giving a brief introduction to the EU-SysFlex project, followed by a quick outline of the work package 3. I will introduce the speakers that will discuss their own individual research topics, which can be seen independently, but of course they also fit in the bigger questions treated in the tasks and the work package. The task leader will close the presentation by bringing together conclusions based on the individual subtopics. You see the deliverable that is under final review and hopefully published soon on the website of the project. The models today have all one thing in common. They are deployed to study a European power system in the middle of a transition. Increasing the current shares of renewable energy sources from today's level of about 30%, we will go to systems well beyond 50% in 2030 and further in the future. This has some significant challenges of the operation of the power system. It is the goal of this study to incorporate as much as possible large shares of non-synchronous electricity sources. EU-SysFlex stands for Pan-European System with the efficient coordinated use of flexibility for the integration of a large share of renewable energy sources. As such, it is the aim of the project to come up with the new types of services that will be needed to meet the system needs, but also to facilitate the integration of renewables. In the technical context depicted here, a range of products and services is proposed to cover the range of technical system needs identified by other work packages. The link between regulatory barriers or market design options and product characteristics is studied by this work package. We study the organization of markets, regulatory frameworks, and innovative system services. The conclusions of work package 3 will support the construction of a flexibility roadmap on the one hand and help design innovative business model on the other hand. Work package 3 is situated in a total of 12 work packages, out of which 4 have a demonstrator showing the innovative services being brought into practice. On this slide, you see the organization of the work package more in detail and the 4 tasks and how they link among each other. While basing our work on the identified technical scarcities from work package 3, the work of work package 2, the work of work package 3 serves also as input for the business model creation and business case calculation of each individual demo and of work package 11. Moreover, as said before, the results find their way in the flexibility roadmap for a future European power system. The work is almost finished, and what you see today are the results of 2.5 years' work. Each of the tasks will soon have their final deliverable available publicly. We have a busy agenda today, and in total of 9 speakers from 5 different research centers will present their results today. The group of Professor Erik Delary has done fantastic work in leading this task, and I give now the floor to the task leader, Arne van Stiphout, to further introduce the objectives of the task 3.4.
Thank you, Hans-Peter, for your introduction, and also welcome from me to everyone to our webinar on task 3.4. I will indeed kick us off today by introducing task 3.4 that we from KU Leuven have led, myself together with Professor Delarue and also colleague Chris Poncelet. Let me briefly come back to the slide that Hans-Peter has already shown to set the context a little more sharply. The main interaction we had in task 3.4 was with task 3.2. The focus of that task was on the organization of markets and regulations to facilitate innovative system services, the looking at role models and interactions that would happen in the provision of those system services, and also really benchmarking designs so that issues of implementation could be identified and overcome. And from there follows the objective of task 3.4. Which we see on the next slide. So the objective of our task was to complement the designs that came out of task 3.2 by studying with advanced power system and market modeling the different designs that were proposed to look at both their short-term impacts on an operational scale, but also their long-term impacts on the investments that should happen within the pan-European power system. As we will see today, there's quite a broad range of different studies we've done to approach this question, but underlying that were a couple of common elements in the approach I want to highlight here quickly before we dive into the specifics. On the first hand, as Hans-Peter already hinted at, the context was one of a highly renewable EU-28 power system. And as you see on the right side of this slide, there were two scenarios developed under the EU-SysFlex project, one named Energy Transition, mimicking year 2030, and one named Renewable Ambition, mimicking the year 2050, where we see shares of variable renewables. This is of 38 to 48%. In addition, there's around 10 percentage points of biomass, but really the goal here was to stress test these designs under high shares of non-synchronous generations, and most of the research topics really took these scenarios or made certain modifications or adaptations to them appropriate to the research question. Second common point is that the focus was on the operational time frame. So really looking at effects on the second, minute, or hour level, and then also thinking about what the long-term effects of those impacts could be. And all of this in the context of power system reliability. How do these designs interact with maintaining the current levels of power system reliability, but then in the context of a highly renewable power system. And then also the tools, as mentioned in the objective already, the goal really was to use advanced modeling techniques to analyze all this. So we see some unit commitment and economic dispatch models, as well as scheme theoretic approaches, agent-based approaches, and so on, where always the approach was to benchmark these new designs that were proposed with an ideal fully integrated market regulatory setting, such that we could see actually how close designs were able to bring us to this ideal situation. There were roughly 4 areas of focus that we can cluster the work in. I'm going to briefly go over them here and also link them to the chapters in the report that actually touch upon them, so that later for your reference, you can really go and look for the topics that are closest to your interest in this specific research. Firstly, of course, market and regulatory design, where we looked at integrated markets versus sequential markets, also things like the ability for new technologies to participate in these new markets, and then some market parameters such as clearing frequency, temporal resolution, and so on. And we have 4 chapters that really dive into some of those aspects. Second element is market behavior. So things like the market participant decision-making in these multi-service markets, but also the potential for strategic behavior in system service provision. And we have 2 chapters that touched upon those aspects. A third area of research was the geographical aspects to all of this. So locality of system services, where are these units located that provide the system services, and how does that impact their ability to do so? So things definitely like TSO-DSO coordination, but also cross-border exchange of flexibility services and how interconnections either enable or constrain these things. And then further coordination, such as congestion management that happens across borders, 3 chapters looking into those. And finally, the long-term effects that I mentioned before, the investment effects. In this case, how are these short-term markets really giving long-term investment signals? What fall from that? But then also complicated questions related to the allocation of costs and benefits, especially when we're thinking about cross-border coordination and investment. Again, 2 chapters that touch upon those points. So let me wrap up this introduction briefly with giving you an overview of all the chapters that are in the report. I've highlighted here in green these elements that relate to these focus areas of the task as a whole. And also again in blue, that really it was about taking all of these focus areas and stressing them in these highly renewable systems. We're gonna touch on almost all of these chapters today, but as we have, as Hans-Peter said, a busy agenda, it will be mostly to give you a flavor of the research that has happened so that later on you can follow up with the people who have authored specific chapters according to your own personal research interests. So with the stage set, I would suggest that we simply dive in, and we do so with the first content chapter, which I will present to you myself. Now, this was a combination of 2 chapters, actually, research on market integration, notably on energy and reserve products. So there are 2 chapters that relate to this in the report. The first one looking more at within border integration, the second looking at cross-border integration. And so just as we start, a bit of context as to why we wanted to look in this specifically. 2 elements to this. On the one hand, an operational context. So there are clear opportunities here within border integration. We obviously think of the fact that the scheduling of energy and reserves are interdependent. And so there are some opportunities in co-optimizing their scheduling, but then also cross-border, where there are some spatial effects, for example, spatial smoothing, which allows us to reduce reserve requirements, spatial arbitrage, so we can more efficiently allocate reserves when we're cooperating across borders, and also some increased opportunities for imbalance netting and reserve exchange in real time. On the other hand, there is an institutional context where these opportunities are being recognized and are being moved upon or trying to be taken advantage of. We have the Commission regulation on establishing a guideline of electricity balancing, but then also the related all-TSO's proposal for a methodology for the co-optimized allocation process of cross-zonal capacity for the exchange or sharing of reserves. So briefly summarized, there are some operational opportunities here, and there is some institutional interest to really start taking advantage of them. Part of our research here was to look at those opportunities and try to quantify the benefits of them in a little more detail. On the next slide, we see the first opportunity for integration, which is within border integration. Now, a brief sketch here, outline of the process of the markets moving from the before day-ahead stages to the real-time stage. And the focus here really was on this day-ahead scheduling of first the energy day-ahead market clearing and then the reserve allocation. Now, in Europe, this is a sequential process, whereas in the United States, this is already a joint process. The main thing to recognize here, and this is what chapter 4 studied, is that you don't need centrally cleared markets to actually make this a simultaneous market clearing and take advantage of the opportunities of co-optimizing both markets. Another element, a possible element of integration, as I said, is cross-border integration, where we really think about the reserve side of things. So there's the sizing, procurement, and activation, which historically have been uncoordinated. But now in recent times, there is already some coordination ongoing on the activation side with the projects that are listed here. And then there is also now some action to sort of plan action on coordination on procurement. And it's from this stage that things also get a little more complicated, because then we need to start to allocate cross-zonal capacity on the day-ahead stage at the latest, which then impacts the availability of this capacity for day-ahead and intraday energy markets. And then one step further than what we call here reserve exchange is reserve sharing, where there isn't much action yet, which is really when we go further and undertake a joint sizing requirement. And there, we're really in the earliest stages. There's a little bit of movement, obviously, in the Nordics and some bilateral reserve sharing, but really at a European scale, we're still to take advantage of this. This is what we studied in chapter 6. We're not going to touch upon that much more here, but really look at some of the work we did in chapter 4 and give you a flavor of the modeling we did and some of the main results. So a very brief outline of our methodology here. We took this joint versus sequential market setup and we took it in a full unit commitment and economic dispatch model. So all technical constraints, minimum up and down times, ramping, etc. And then coupled this day ahead to the real time, to an activation phase where we set base and medium load generation units to have their commitment decisions fixed, have also the economic dispatch of the base units fixed, and then had these two types of market setup where we had joint versus sequential, where in the sequential case, the day-ahead energy market does not anticipate the day-ahead reserve market, and in between those two market clearings, base and medium load units could not start up to then provide more reserves. We also finally added the opportunity for load and renewables to contribute reserves, upward and downward in this case, a simplified approach to just see if there were reserve shortages that were following from this non-optimized sequential behavior, whether we would need to use these other kinds of resources and then look at the costs associated to that. We took this model and methodology setup and applied it to a case study that focused on the CWE region, went through a full year in 15-minute increments with 365 daily optimizations, moving the window along, took a trade-based network constraint approach, looking at one node per zone, and then applied it in 3 scenarios, so a current system, and then the 2 EU-SysFlex scenarios, which we complemented with some additional information to really get down to the unit level and being able to see scheduling and technical information on a unit level basis. And so then to conclude, I just want to highlight some of the main results that we saw coming from this. First of all, what you see on the right side is some result graphs that on the x-axis show an increasing share of wind and solar, so really the non-synchronous renewable sources. And on the y-axis, you see the cost difference between a sequential and a joint approach. And perhaps unsurprisingly, what we see is really that the additional cost of sequential energy reserve markets increases, but does so more than linearly as we get more and more renewables, as we have to turn to more expensive source of reserves and just need more reserves, obviously, in general. Second element that we then looked at is what if we allow for some more alternative sources of reserves? So that's the graph you see below, where we played with the cost of scheduling load and renewables, just as a sort of representative technology to see what could be achieved if other types of technologies were allowed to participate. And then what you see is that there is a potential for these new types of reserves to offset some of these increasing costs. So this is really, even in a joint clearing mechanism or sequential, even in a sequential clearing mechanism, when we allow other technologies to start participating, we can decrease the additional cost that comes with not having this being integrated market operation. So then to wrap up some takeaways, 3 main ones. What we found is that, unsurprisingly, market integration can reduce the cost of ensuring reliability in highly renewable systems. As I showed previously on the slides just before, within border integration, we see the effect of sequential to joint markets. But then in chapter 6, we also explored the potential for cross-border integration, noting that there, of course, there is the additional challenge of harmonization. We see, secondly, that alternative providers have to play an increasing role in reserve provision, as they can partially offset the cost increase of ensuring reliability in high renewable energy systems. And last but not least, we see that it is important to act on these insights sooner rather than later, because as renewables will increase, the cost of not acting will too. So with that, I wrap up my presentation, and I will pass the word to Professor Eric Delarue to present the results of chapter 5.
Okay, thank you, Ayana. So also good morning, everyone, from my side. I will be talking about the temporal granularity of joint energy and reserve markets. So as Ayana already outlined, with the increasing penetration of intermittent renewables, an efficient, let's say, planning and operation of flexibility becomes very important. And in this contribution, we in fact aim to assess the impact of the temporal granularity of reserve markets and total cost. So in European systems, it is the transmission system operator, the TSO, that currently procures and deploys flexibility in the form of operating reserves. And in fact, we can distinguish 3 phases in this process, and those are indicated by the boxes with the blue edges that you see at the bottom of the slide. So the first one is the sizing or the dimensioning of the needed reserve capacity. Second is the procurement or the allocation of reserves. And the third is the activation of the reserves in real time. Now, the temporal granularity of these reserve markets is determined by, let's say, on the one hand, the frequency, that is how often reserves are being sized and procured or allocated, and the resolution, and that is the length of the sizing and the procurement blocks, in fact. And in this contribution, we focus on the uncertainty related to wind power, and we assess the benefits in terms of cost associated with increasing the temporal granularity of reserve markets in high renewable systems. So on this slide, we show a bit more of the model and the case study, but I think, Hans-Peter, we missed a slide. Could you go back one slide? Yes, this is the one I wanted to show. So here we show a bit more specifically the 4 considered temporal aspects of reserve markets that we are analyzing. So 2 are related to frequency and 2 to resolution, combined with sizing and allocation. So the first one, number 1, is the reserve sizing frequency, and that specifies how regularly reserves are being sized. So on the figure here at the bottom, which is just an example for a 2-day period, you see the sizing, the reserve sizing frequency, which happens on a daily basis, meaning that every day we size the reserves for the next day. Then second is the reserve sizing resolution. This basically sets the length or the granularity of the sizing blocks. And on this figure, this resolution is in blocks of 3 hours. Then third is the reserve procurement frequency. This basically sets how regularly reserves are being procured. On the figure, this is not explicitly shown, but in this case, it was kind of synchronous with the reserve sizing, so on a daily basis. And then fourth is the reserve procurement contract duration, and that specifies the resolution of the reserve products being allocated at unit level. So that is the length of the procurement blocks. And on the figure, this reserve procurement contract duration is 50 minutes, meaning that in this case, a unit could contribute to reserves during just 1/4 of an hour. So it are these 4 temporal aspects that we will vary and of which we will try to assess the impact. Now we can move to the next slide. Thank you, Hans-Peter. So then quickly on the model. So we deployed a classic mixed integer unit commitment economic dispatch model. So given a set of power plants, the model determines basically how we're going to schedule and then operate the power plants to meet a given demand at lowest cost. And in this case, the model is set up with a rolling horizon approach, which allows to represent joint energy and reserve market clearing under forecast conditions, and then later do an actual dispatch when the uncertainty, and that's wind in this case, is being revealed. And this then, in fact, represents the reserve activation or the balancing. So the rolling horizon optimization allows to adjust the frequency and the resolution of the reserve sizing and allocation. I will illustrate this process on the next slide a bit more. Then very quickly on the case study setup. Still this one. So we focused on the Belgian power system. We did a 1-year simulation. We used 2 systems coming from the EU-SysFlex scenario, so the energy transition and the renewable ambition. And we then further made use of renewables and demand time series of the year 2018 coming from the Belgian TSO. Okay, and then we can go to the next slide. So here a bit more on the functioning of the rolling horizon approach. So as we progress in time, basically we do subsequent optimizations, and then with each time updated forecasts on wind power become available. Hans-Peter, if you progress a bit on the slide, yes, then I will show some explanations. So period A in this case represents, in fact, the balancing stage. This is where there is no more uncertainty, and then the allocated reserves can be used to deal with forecast errors. So the commitment statuses of power plants are given from the previous optimization, and those are being set fixed. Now, when we proceed through time, as I said, we can make use of updated wind power forecast, and that is what I would show on the right-hand side. Yes, that's here. So based on historical wind power forecast data, we kind of constructed this wind power forecast scenario generation tool. And the shorter the forecast lead time, that is, the closer we are to real time, the better the forecast becomes. Okay, then we can go to the next slide. So to recall, we focus on those 4 different aspects of the temporal granularity of reserve markets, again shown here at the bottom. And in this contribution, we focused on 6 cases, that is 6 combinations of those 4 temporal granularity aspects, and the combinations are shown here in the table, going from the most conservative on the left to the most dynamic case on the right. And in the most dynamic case, we in fact have an hourly market clearing and a resolution of 50 minutes. And the arrows in the table, in fact, each time show what changes from one case to the next. Okay, and let's then enter into some of the results. Again, just to give you a flavor. So focus here is on the total operational cost. So on the figure, we see the cost for the 2 systems that we considered, so left and right, and then each time for the 6 cases, and here expressed in relative terms, so relative to the most conservative setting, that is case 1, which is each time depicted on the left. So in both systems, we see a gradual decrease when going from left to right, when giving reserve markets a finer temporal granularity. And especially sizing the reserves more frequently from, for instance, daily to hourly level, that leads to significant cost reductions. That's on the graph growing from case 5 to case 6. And the main driver of these cost savings is the reduced wind power uncertainty associated with the shorter forecast lead times. And as a result of that, the final planning is just made under less wind power forecast uncertainty, as the reserves are sized and procured on a more frequent basis. Then quickly to wrap up and then provide some takeaways and some conclusions. So we analyzed 4 different aspects of temporal granularity of reserve markets. And that is how more dynamic markets could bring cost benefits. And if we look at the impact of more dynamic reserve sizing frequency and reserve sizing resolution, then we find cost savings between 0.75 till 1.1%. When looking at the impact of a more dynamic reserve procurement frequency and contract duration, we find cost savings of about 0.75%. Now, of course, the actual implementation of very highly dynamic reserve markets could also pose challenges, obviously. So think of timing difficulties, just as acting on updated forecast information and also communicating to the TSO. And also the TSO might perceive more risk when reserves are contracted on shorter basis, on a daily or an hourly basis. But overall, it's clear that this research also supports the call towards shorter term and higher resolution reserve markets. So with this, I'd like to finish this part of the overall presentation, so of this contribution. Thank you for listening. And then I would like to give the word now to Gwen Williams from Vito Energyville to continue. Thank you.
Thank you, Erik. So my name is Gwen and I work at Vito Energyville as a researcher on energy markets. Together with my colleagues Hans-Peter Huschle, Yuting Mao, and Carlo Manna, we conducted a study titled Increasing Technology Neutrality in Service Markets in Power Systems with High Risk Shares. And I think the best way of explaining what our study is about is to start with explaining the title. So there's 3 main concepts in the title. The first one is power systems with high shares of risk. So as Hans-Peter already mentioned before, it has been projected that there will be a significant increase in the installed capacity of wind and solar. And then the second concept is service markets. So as wind and solar are variable in generation, there will be an increased need for service markets, for instance, balancing markets to maintain frequency stability. And then the third concept, technology neutrality. So coming back to these balancing markets, the European Electricity Balancing Guideline states that participation in balancing markets should be technology neutral. So that means that there should be an increasing role for RES. However, in many countries, wind and solar, they currently only contribute in a limited way to the service markets. And this then further limits the ability of the power system to accommodate more RES. The graph below shows that there can be a big gap between the installed capacity of technologies on the one hand and their technical and their market potential on the other hand. And this is also the case for wind and solar. As I said before, they do not contribute significantly to service markets now, even though research has shown that their participation in these markets is actually technically feasible. So if we have the installed capacity of RES and the technical potential, the question that we can ask is, how can we increase the market potential? And in our study, we look at this question from the position of electricity market design. And more specifically, we focused on the design of the balancing market, in this case, the tertiary reserve or MFRR market. And we also focus on how market participants behave in this market. If we model the markets, then we can find out which barriers to participation exist and how we can improve the market setup to tap this big share of technical potential. We can go to the next slide. So to be able to model the markets and assess the market potential of technologies, we developed an agent-based market simulator. And in this simulator, we can include different bidding optimization techniques in one single optimization tool. And we can also add a very detailed representation of the market products and associated market clearing. And by doing this, we can then see how this technical potential is translated into economic and market potential. The simulator itself is built up around three main blocks. First of all, on the right side, you can click on Peter, we have the market operator block. So this block looks at the product and market characteristics. And here we can include technical details in the product. We can test out different products and auctioning mechanisms, and we can look at product specification and market liquidity. And this way we can see which product and market characteristics deliver the best offers for the technical need. Then on the left side, you can see the market participant block. This is where the bids are generated. And here in this block, we want to capture when a decision is taken by the participants and which information is available to them. And also, because we include different markets in one simulation, we need to know how participation in one market, for instance, MFRR, influences participation in a consecutive market, for instance, the day-ahead market. The market participant block, it contains the bid generator, and this implements the bidding strategies of the market participants. So in this, the figure below, you can see the structure of the bid generator for the MFRR and the day-ahead market. And then finally, the middle block, that is the actual simulator. And this one is in control of the flow of information and also the execution of the dynamic event calendar, of which you can see an example below. Here, we have the structure for the calendar for weekly MFRR auction together with the daily day-ahead auction. Then if we move to the next slide, so here, this is about the case study that we did. So we developed a market simulator, and then for EU-SysFlex, we developed a specific case where we look at the impact of shortening the MFRR procurement cycle on the offered market potential from wind and solar. And we applied this to Belgium. So here with the procurement cycle, we mean how often and for how long capacity is reserved to participate in the market. And we simulated daily, weekly, and monthly procurement cycles, and then we compared the outcomes. And here, the daily procurement consists of 6 blocks of 4 hours each. Then the next slide shows the results. And here we look at the results from a technologies perspective. And more specifically, if we look at the offered average capacity of RES, this is solar and wind, in function of the frequency of procurement, so daily, weekly, and monthly, we can see that the largest amount of capacity is offered in the daily auction. And also we can see that these intermediate solutions here, the weekly auctions, they only have a limited impact. However, if we compare this market potential to the total installed capacity, we can see that there is still a big difference between the two, meaning that we have to look for further market design improvements to tap more of the technical potential. And then the second graph shows the seasonal impact of the offered capacity, or seasonal impact on the offered capacity. And we can see here that actually seasonal changes also need to be aligned with seasonal needs. For instance, we could do dynamic reserve sizing. And then, so as this supply is more volatile, you can also see that in the next slide, which shows a histogram of the average cleared reservation price. If we compare histograms here for the daily and the monthly procurement, we can see two effects. First of all, there is a higher diversity in prices when we go from monthly to daily procurement, and also there is a shift to cheaper prices when we move from a monthly to a daily procurement. So what are the lessons learned from our study? Next, please. To summarize, we looked at how we can make service markets more technology neutral to include and increase the participation of RES. And to do this, we developed a market simulator and we applied it to a specific case study for Belgium, where we looked at the impact of changing the procurement frequency on RES participation in the MFRR market. And there's a number of things that we can conclude from our study. First of all, a lot of progress has been made to increase the technical potential of RES to deliver system services. However, it's also important to think how we can translate this technical potential into market potential. And then there's two aspects to this. First of all, if we want RES to participate in the service market, the system needs to change substantially. As we saw before in the results slide, going from monthly to daily procurement had a big impact on the offered capacity. And then second, we need to also look into this question of whether technologies cannot participate or if they do not want to participate because it's economically not interesting. For instance, maybe they don't want to participate because there is a cost associated with the loss of green energy certificates by participating in service markets. And this is something that we will look into in future research. And also we plan to focus further on daily procurement, but this time instead of 4-hour blocks, blocks of 1 or 2 hours. Finally, we can conclude that the market simulator allows to capture both the product characteristics of system services and the decision-making of the participants who interact with the markets. And that makes it, to us, a valuable tool. If you have any questions about the presentation or the research, you can contact me through the email address that I mentioned below. And we now move to the next speaker, Danny Pugianto from Imperial College London.
Thank you very much, Gwen. Good morning, everyone. My name is Danny Pugianto. And today I will present our work addressing the need to enhance DSO coordination in order to facilitate market access for distributed energy resources. The previous speakers have described perfectly the need for the energy and ancillary service market integration in a system with high-res penetration. But with increased penetration of distributed energy and flexibility resources, can you just go to next? Yeah. The providers of energy and services will be shifted from transmission connected to distributed connected resources. And the key question before us is how to use these resources in an optimal manner. So a stronger planning and control coordination, or we call it as a whole system approach, between the national transmission system operator and distribution system operators is therefore vital to ensure the optimal usage of those resources and to manage the synergies and conflicts across different applications and objectives. So the graph on the left illustrates that if DERs are used only by DSO, some of the DSO-centric case, then the overall system benefit will be less than half of the potential benefit if the whole system approach is applied, although the saving in distribution capex are larger. Similarly, in the TSO-centric approach, where DERs are used by TSO without considering the need of distribution, the solution will be suboptimal, and it will also require more distribution network to be built. So the challenge is how to maximize the synergies and prevent conflicts between TSO and DSO when they use these distributed energy resources. The next slide, please. So in this work, we have investigated two approaches. One is a centralized market where all energy and service providers and the users are met in a single marketplace. And the second one, the alternative solution, is to have a decentralized markets where the local markets are created to support the national markets. In this context, the DSO will be the interface between the TSO and DER using the virtual power plant concept, of which I will explain very shortly. We will also see in the next few slides the key findings from studying the VPP characteristics and its application to solve transmission problems, the importance of distribution network control optimization, and the comparison between the centralized and the whole system approach. Next slide, please. So in the decentralized multi-stage energy and ancillary service markets, local markets are created with the DSO as the user of the services and DERs as the providers, as you can see on the box there on the top. The remaining energy and service capacity from DERs will then be offered to national market through DSO as the interface. This will be presented as a large-scale virtual power plant, which take into account all DER capacity and also local distribution network constraints. DER services via the virtual power plants will then compete with other energy and flexibility sources in the national markets on the level of playing field. In this case, the national market clearing process may involve transmission system model, but not distribution model as they already considered during the construction of the VPP. Next slide, please. The VPP characteristics can be evaluated using a sequential optimal power flow approach, as we use, where the feasible operating region and the cost characteristics of using the services can be determined. The left diagram illustrates the process of the approach, using the network load generation data and also the prices requested by DERs for providing their services. We can analyze the active and reactive power capability of the VPP, including their ancillary service capability, and at the same time, we can determine the merit order dispatch. The center top diagram shows the distribution network test system we use in the study. The system is based on a real distribution system, but with the substantially increased penetration of REST to be aligned with the SysFlex scenario. The right top diagram shows the PQ capability of the VPP with the upward and downward reserve capability. It is important to highlight that the VPP characteristics will be more dynamic compared to traditional plants, as is affected by demand, DER availability, local constraints, faults, and the network control settings. The approach can also be used to identify if there is any local market power given the location aspect of the DERs. Next slide, please. So one of our key findings is that by optimizing distribution network control, for example, transformer and reactive compensator settings, it can improve the access of for the DER capacity as well as the capacity of distribution network assets to provide services to TSO. For example, the PQ curve of the distribution using tap and reactive compensation optimization will have a larger reactive power range compared to the non-smart distribution system. This highlights also the role of DSO to optimize the local network, not only for their own objectives, such as network congestion management or losses minimization, but also to enable more access to the service capacity that can be offered to TSO. This also triggered discussion and potentially business case for the DSO to offer their services to transmission if there is a suitable commercial framework in place. Next slide, please. On this slide, I show you one of our studies implementing the use of VPP to solve transmission voltage problems. For this study, we used the southwest part of the GB transmission systems when there is a double circuit maintenance exposing via the transmission corridor to network problems. So the right top diagram shows that the line fault between bus 4 and 5, for example, can trigger an undervoltage problem. The right center diagram shows that the traditional solution where the OCGT unit needs to be used to prevent or to restore voltage. However, the OCGT will also need to operate at its minimum stable generation, which normally increase the cost. The bottom diagram shows the alternative solution using the DER services using the VPP, which is found to be much cheaper than the traditional solution. Maybe it can be expected that our study also finds that the value of reactive power services is location specific, as we already know. And in this context, it is beneficial for enabling DER to provide such service due to their geographical advantages. DER will also improve the market competition and reduce the market power as shown in the examples. So the next slide, please. So the last slide shows a table comparing key features that need attention from both incremental and whole system approach. The incremental approach is more pragmatic, suitable with the current system operational structure with the split DSO organization, but it needs to be operated in a smart way to optimize the access and the value of the to the whole system. The whole system approach will be more complex, computationally intensive, as it involves modeling distribution system from street level to transmission and different scale of resources from kilowatt to gigawatt. But it is optimal from system perspective. May not be optimal from individual operator perspective though. So I will finish my presentation at this point. Welcome any questions you may have. You can also send me an email with your questions. So I will then pass the floor to Andika as the next presenter. Thank you.
Okay. So good morning, everyone. So I'm going to make the next presentation together with my colleagues, Marcin Jakubek and Michał Kłos. The topic of the presentation is cross-border coordination. Next, please. Yeah. So let me introduce you first to the topic about cross-border congestion management. So the TSOs are responsible of relieving the congestions on their own area. However, the congestions of the cross-border lines and close to the cross-border lines are more difficult to relieve since they depend on other TSOs' actions. In addition, as you can see in the picture, the planned flows might not always match the actual flows. Therefore, the TSOs should be able to react to relieve those congestions. Next, please. Yeah. So currently, the responsibility of relieving the cross-border congestions is shared between two TSOs. They usually perform manual and iterative inter-TSOs remedial actions to relieve those congestions based on non-harmonized bilateral agreements. And in the case that they can't relieve the congestion by themselves, because they don't have enough remedial actions, they could call for multilateral remedial actions involving another third TSO. However, now the European Union is pushing the TSOs to coordinate the remedial actions in a more cost-optimal way, in such a way that if redispatching a third party should be triggered if it is more efficient. Of course, the involvement of the third party requires the proper harmonized design of the cost-sharing framework to be able to incentivize that third party. Inside the cross-border congestion management topic, our scope is focused on the phase shifter investments to release the cross-border congestions. Why phase shifters? Because they are one of the most attractive remedial actions for the operator due to their effectiveness to relieve cross-border congestions. The TSOs should adapt their investment decision process to the new coordinated framework. Therefore, in our research, we have addressed two related questions for that. The first one, where should we build the phase shifters, considering that the best location might be placed outside the TSO area? And the second question, who should pay for those phase shifter investments? In the following slides, my colleagues will answer those questions.
Hello, I'm Marcin Jakubek from NCNR, and first I would like to back up Andika's comment that PSTs are really a good tool for relieving congestions. The map on the next slide shows the severity of the cross-border congestions, the yellow lines, we encountered in the 24 SysFlex scenarios. Below, we report the cost of relieving the congestions derived by our congestion management tool. The cost is around 12,000 euros when we use the existing PSTs, and more than 10th of that if we would not have them in the system, and all would have to be cleared by redispatching only. Thus, we see that PSTs are really a valuable asset. over the next slide, I will say a few words. What do we mean by preselection of the location for new PST investment? So in the European system, we have thousands of branches, and each could be treated as potential candidate for extending it with a PST on one end or the other. The traditional methods for evaluating the potential with investments are computationally demanding. They go through the whole market process and verify the benefits on the new grid state with enabled investment. So what we want to do here is to use rather the information from the current state of the grid, meaning the current topology, current market solution, and current cross-border measurement solution, in order to identify a short list of candidate locations. This short list could be then treated as an input to more computationally demanding methods I mentioned earlier to evaluate the candidates further. Therefore, we aim to provide a decision support methodology that helps to reveal the potential investment location. So in terms of the methodology of the preselection, during SysFlex project, we have came up with two methods, both of them built on the characteristics of the solutions to the cross-border congestion management problem. In both methods, we presume that each branch in the system can be a potential location for a new PST. The first method, presented on the left side, measures the marginal influence of the change in phase shift over any branch in the system on the redispatch costs. The details of the derivation of this measure are in our paper, but I will mention here only that it is connected with the dual variables or Lagrange multipliers associated with constraint on keeping the phase shift over the branch constant in the problem. We have named this measure multiplier indicator. The second method, presented here on the right, measures the sensitivity of power flows over the congested lines on the change in the phase shift over any branch in the system. So again, details are given in the paper, but we look at the phase shift distribution factors, PSDFs for short, and juxtapose it with the congestion volumes. And we derive what we call congestion factor of each possible PST location. And to sum up, so multiplier indicator focuses on how a new PST in a given location would help to decrease the cost of redispatching, while congestion factor, how a new PST in a given location would help to decrease the congestion severity. Going now to the next slide, we have the results of the two methods. The graph on the left side shows the top locations for PST placement using the multiplier indicators. The size of the dot shows the level of the multiplier indicator in each location. And the graph on the right side shows the top locations according to the congestion factors. You can see that both methods point to allocation near the German-Austrian border as the one with the highest MI and CF values. On the next slide, reminding the congestion pattern we deal with here, you can see that on the first side, the congestion on German-Austrian border does not seem too severe compared to some other borders, particularly Polish-German and Polish-Czech. However, it turns out that the congestion near the German-Austrian border are the hardest or the most costly to address using the existing remedial actions. So the next slide, as a test of the methodology, we put the new PST in the location with the highest MI and CF values. And next slide, please. We solve the congestion management problem once again, but with the new PST in place. And the total cost of congestion management decreased dramatically, making it almost cost-free across all 24 scenarios. So on an ending note, we also calculated the congestion management cost in case of not only the top one, but the second best candidate, third best candidate, etc. In total, we analyzed 13 locations, and in neither of those we experienced such a dramatic decrease in cost as in the case of the top candidate. Reminding that we are only in the pre-selection phase, we are aware that there would be a need to use this input into a more detailed study that uses more computationally demanding methods, but we hope that this direction is as a pre-selection, these two methods seems to work nicely. So this is the end of the pre-selection topic, and now I give floor to Michał for the discussion about investment shares. Thank you very much.
Okay, hello everyone. Thank you, Marcin. The purpose of my slot is to take the message from Marcin about the optimal locations for pre-selected phase shifters, and asking the question of the proper way of funding, providing the funds for installing them in a grid. So generally speaking, the first clue here is that we are going to consider avoided costs of remedial actions to recognize beneficiaries of such investment and, briefly speaking, turn them into investors. The costs of remedial actions follow the draft of proposal of core operators, which work on the methodology for future cost sharing pattern. And the second clue here is that we are trying to associate the costs with the zones according to polluter pays principle. It is rather about determining the causer of congestion than letting the owner of the infrastructure take responsibility for alleviating the stress, the congestion. Next slide, please. So in order to find the reasonable, justifiable cost sharing pattern, we need to answer several supplementary questions. Those questions are somehow guided by core operators guide proposal. And here the basic top questions we have, the top question is which network element generate costs? And once we have this one, we can try to follow two paths of reasoning. The right one is a cost related path. And here we try to answer the question about the optimal solution. This is what Marcin done. And then how to divide the cost into particular network elements. And on the left side of the picture, we have the causal related path. Here we can ask the questions about the responsible zones, which zones actually are the ones who cause the overloads, and then how to divide the costs generated by particular element into particular zones. If we combine two paths, left and right, then we can answer the question about the particular monetary burden of zones. And once we have this, we can answer the question about the greatest beneficiaries, and then how to actually divide the investment costs. All the blue elements are somehow drafted or postulated by the core proposal, but we have actually implemented the exemplary way how to introduce them into reality and how to compute them. And the conceptualization of the investment matter is developed within the SysFlex original. Next slide, please. Okay, so we want to test the approach by performing the investment share analysis for two possible locations of PST. First is cost optimal according to pre-selection described by Marcin, and this is the German-Austrian position. The second one is suboptimal or non-optimal, but also interesting for the reasoning that we are showing you here. So below we can see, next slide please. Below we can see the concept somehow written into equation. It is very basic idea. In denominator we have the savings described by Marcin and put into the table, and in the numerator we have the result of cost sharing analysis. So here we can actually recognize the benefit of particular zone, and this benefit divided by all the costs, all the benefits, would be the indicator for the candidate for investment share in our situation. Next slide. Okay, and how do we obtain the results? So here is a set of pictures which guide us through the computational difficulties or challenges over here. So first of all, we need to take a multiple snapshots. Probably it could be, for example, hourly simulation of the whole year. For the purpose of the analysis, we took 24 snapshots representing separate hours. And if we follow the cost sharing path that I introduced before, we can find the picture which shows how actually costs are generated on particular borders. Here we have the highlighted example of Polish-Czech border across the time, across the particular timestamps. And in our case, the magnitude of overload is proportional to the cost associated with particular branch. Below, we have causal related path. So here we try to actually answer the question, who is the main responsible party for causing the congestions? And we can see that on average, Germany seems to be the most significant causer of majority of flows in the region, so that the overloads as well. On the third picture, we have the already computed zonal savings, and we can see that the savings of the red one, so German-Austrian situation, are greater than Polish-Czech, depicted in yellow color. And if we turn those savings into particular shares, we can see two bars on the right bottom corner, and those are actually images which show the proposal of cost sharing for two investments. On the next slide, we can see those numbers put into the map, and we can draw several interesting conclusions here. First of all, we can see that the beneficiaries, the greatest beneficiaries, can be quite far away from the investments. We can see that this is an example of Germany, for example, which is quite far away from Polish-Czech border, but still takes the greatest share of this investment. We can see that the method was somehow applied to investigation of PSTS locations, but it can be extended to different network elements. So it is not limited to only this example. It is also important to highlight that the method is independent from the particular solution of cost sharing. It is only applied based on one pattern, but it can be adapted to any future solution. And in the end, I would like to highlight that it is somehow consistent with the new regulations which are to come in the next years. So it would be all for cost sharing investigation, and I would like to pass the floor to Chiara from UCD.
Good morning. So my name is Ciara O'Dwyer from University College Dublin, and I will be presenting our work on long-term investments and ancillary services markets. So new system services are being proposed and introduced around the world in response to increasing shares of variable renewable generation. This work today examines the impact these services have on long-term investments. We address the level of detail required in investment models. We also examine the impact these services have on portfolio development and how this affects system operating costs, curtailment levels, and emissions. For this work, we used Ireland as a test case. The two scenarios have high levels of variable renewable generation. So steady evolution has roughly 50% and low carbon living has over 60% variable renewable generation. These align with the two of the network sensitivity scenarios from work package 2. So next slide. So for this work, we used Backbone, an energy system model, which was developed by VTT in Finland. It's a flexible model which facilitates both investments and operational optimization using common input data. The level of detail, both temporal and operational, is user-defined and can change over the course of the simulation. This allows us to balance model complexity against computational effort, so it's very well suited to this task. Next slide. So in the simulations, the renewable generation was pre-selected according to the scenarios, either steady evolution or low carbon living. And we used representative weeks, which were selected using a time slice tool, which was developed by KU Leuven. The investment options within the model are OCGT, CCGT, and grid-scale batteries. So the objective function considers fuel and carbon costs, variable operational and maintenance costs, startup costs, and then in the investment model, it also considers the capital costs of the investment options. So the typical unit constraints are considered, and also an inertial floor is introduced, which comes into play at very high penetrations of wind and solar. So we also then looked at 5 reserve scenarios. So starting at A, within the investment model, no reserves are considered in reserve scenario A, which is typical of many investment models. Then in scenario B, POR is introduced, so one of the original reserves in Ireland. And then after that, we introduced 2 new system services, fast frequency response and a 1-hour ramping product, which are introduced individually. And then finally, reserve scenario E has all 3 of the reserve products together at the investment stage. Next slide. So a quick overview of the results. So this graph shows the investment technologies, the investment capacities in the different technologies for the different reserve scenarios, starting with steady evolution. So a reminder, reserve scenario A, no reserve was considered at the investment stage, and most of the new capacity is in CCGT, which is the least flexible unit in terms of startups, ramping and reserve provision. Very low levels of investments in batteries occurred despite the high levels of renewables that we're considering and the detailed chronology. So load shifting alone does not justify significant investments in batteries for the steady evolution scenario. When we move to reserve scenarios B to E, there's a shift to more flexible technologies. So when fast frequency response is introduced, so reserve scenario C, there's a shift towards batteries, while when the ramping product in reserve scenario D is introduced, there's a shift towards OCGT, and the most flexible portfolio is produced in reserve scenario E when all products are considered. So portfolio A in the steady evolution scenario is not capable of efficiently providing the required system services. And when we run the schedule model to get a more accurate look at the operational costs and curtailment, it results in the portfolios or reserve scenarios B to E result in operating cost savings of between 12 and 15%, with the lowest costs achieved by the most flexible reserve scenario E, which is also the most expensive, but as operational costs dominate, the overall costs are still lowest for this reserve scenario. So in terms of curtailment, again, reserve scenario A, the least flexible, results in much higher levels of curtailment, approaching 6%, compared to between 2.5% and 3% for the remaining scenarios. And carbon emission reductions of between 3 and 3.5% are achieved from reserve scenarios B through E. Next slide. So we also completed some sensitivity analysis. So there's a great deal of uncertainty surrounding a number of the assumptions. For example, investment costs, particularly for grid scale batteries. When the capital costs are either increased or decreased by 20%, you can see here the changes in investment decisions, with battery capacities increasing significant when the lower costs are assumed. Next slide. We also considered a scenario where the conventional plant has, the investment options have increased flexibility. So the OCGT and CCGT plant have increased ramping capabilities and reserve capabilities and lower minimum generation levels. So in this case, battery investments fall when these more flexible plants are considered for investments. Next slide. There's also uncertainty surrounding the requirements for some of the new services. A DSM reserve scenario assumes that these services can be provided by a fixed level of demand response, which is equivalent to reducing the overall requirements. Scenario C through E see increased investments in CCGT for this DSM reserve sensitivity. Next slide. So for low carbon living, so this is greater than 60% variable renewables. The higher levels of renewables included means that there's already significant battery investment without considering any reserves at the investment stage. So for reserve scenario A. The introduction of fast frequency reserve sees much more modest levels of increased battery investment, while the large requirement for ramping products sees a large shift to OCGT investments in scenarios D and E, facilitating similar overall operating costs, but with much lower investment costs. Next slide. So again, with the sensitivity analysis, we can see large changes in battery investments when alternative capital costs are considered. Next slide. And generally higher CCGT investment when more flexible units are considered or requirements for new products are reduced. Next slide. So in conclusion, this work highlights the importance of operational detail in investment models, although the relative importance is highly system and scenario dependent. The presence of markets for required new products can send clear long-term signals to investors and facilitate the required level of investment in flexible technologies. However, while new products can be of high value, quantities can be small, which must be considered carefully at the market design stage. Thanks. So I'll pass on to the next presenter.
Good morning, everyone. So this is the last topic that we will cover today, and the focus of this work, which has been led by our group in Imperial College, was on market power effects. So moving to the next slide, the motivation in here lies in the fact that despite the introduction of competition in European markets, still most of them are characterized by a relatively small number of large players. And as it is the focus of many market analysis studies, large players can potentially exhibit strategic behavior, meaning that they misreport their techno-economic characteristics in the market clearing process. In other words, exercise market power in order to increase their profits. But this implies, on the other hand, higher price levels for the consumers and loss of social welfare. So the development of models capturing this strategic behavior and analyzing market power effects has been one of the key research areas in electricity markets in the last 2 decades. However, in the context of SysFlex, we focused on 2 particular aspects of market power effect, which we find very relevant for the future European energy system. The first one lies in analyzing the impact of new flexible technologies in the form of flexible demand and energy storage on market efficiency and the market power effects from large producers. And the second, as we move towards more complex bidding mechanisms, as also mentioned before from other speakers, the question is how factoring the unit commitment characteristics of the different generation units, whether this can help strategic producers increase their profits and whether this needs further regulatory attention. So moving to the next slide, the traditional and fundamental methodology in the available literature, and this has been our starting point in here for analyzing market power effects, is by level optimization. And this is a relevant and suitable methodology because it allows us to capture the interactions between the bidding strategies of strategic players, which aim at maximizing their own profit. And this part is modeled in the upper level problem. And on the other hand, on the competitive market clearing process, where the market operator collects bids and offers from different players and clears the market by maximizing social welfare, which is modeled in the lower level problem. The traditional approach, if you can just click once, Hans-Peter, thanks, for solving this kind of problems has been to replace the lower level problem by its equivalent KKT optimality conditions, which are then inserted as constraints in the upper level. However, this approach is relevant and useful only when this lower level problem representing the market clearing process is continuous and strictly convex. So this means that this traditional approach used in the literature in the last decades has been neglecting non-convex characteristics associated with the binary unit commitment decisions of strategic players. So in order to deal with this fundamental challenge, moving to the next slide, one of the key contributions for our work in this SysFlex task has been to develop a new analytical approach in order to factor these unit commitment constraints in the market clearing process. I'm not gonna go due to time limit restrictions in here in the full details, which you can find in this relevant paper we have published within the project. But just to mention, if you can just click twice, thanks, Peter, the fundamental features of this approach lies first on relaxing the unit commitment variables from binary to continuous ones. derive the dual problem of this relaxed market clearing problem. And then in order to make sure that this relaxation does not introduce significant errors in the solution, we penalize sufficiently the duality gap in the final problem. So overall, we transform through this approach the original non-convex bi-level optimization model to a mixed integer linear problem that we can address through commercial solvers. So moving to the next slide, our focus in applying this model has been on a 16-node model of the UK market, where basically in the UK the situation is that most of the renewables with a high availability are located in the north, in Scotland, while the biggest demand centers are located in the southern part in England. And in here we consider a joint energy reserve market with a day ahead horizon, factoring through a DC power flow model the network constraints, and examining different scenarios regarding the presence of flexible demand and energy storage in the system, as well as congestion effects. So moving to the next slide, just to give some of the key results of the studies. The first set of studies focused on analyzing the impact of demand flexibility, and we measured this demand flexibility in here by a parameter alpha, which represents how much of the overall energy consumption can be shifted in time. So what you can see in the upper layer of this slide, despite the assumption that we have done in here that demand shifting basically is energy neutral within a day, meaning that the overall energy consumption remains the same. So basically demand flexibility allows us to flatten the demand profile without reducing the overall energy consumption. In the top right graph, you see a measure of market power, which is how much the price is increased when large producers act strategically and misreport their actual costs. And what we can see is that demand flexibility in here overall helps us reduce this market power effect, particularly because of the highly positive impact during peak hours. These are the key hours in terms of market power, because most of the capacity is fully used and the levels of competitions are reduced. So overall, although the overall energy consumption remains at the same level, the market power exercised by large producers is significantly reduced. And then as a second step, we have carried out studies also with network congestion, which is very important for the analysis of market power, because with network congestion, strategic producers can be isolated from the rest of the competitors in the system. So this analysis, without going to all the details in here, the key findings are that overall network congestion reduces the social welfare, meaning that the extent of market power is enhanced, but also the impact of demand flexibility on reducing this market power effect is location specific. So one of the things we see is that depending on where this demand flexibility is located, the market power of co-located producers is reduced and the benefits for co-located consumers are enhanced. Moving to the next slide, we have also carried out similar type of analysis now for energy storage. The key difference with respect to the flexibility, to the demand flexibility case, is that we examine different scenarios regarding the ownership structure of storage. So we have cases with distributed and large-scale storage. And as you can see, if you can also click in here twice, Hans-Peter, basically with large-scale storage owned by a single large player, the overall profit of storage is enhanced because it can exercise market power to its own benefit. So basically, in both cases of distributed and large-scale storage, in terms of social welfare would get benefits. However, these benefits are enhanced if the same capacity is owned by a large number of small storage players instead of having it all concentrated to one player. And finally, in the next slide, the analysis here was about basically comparing the outcomes for strategic players when they use the state-of-the-art models, which, as I mentioned before, are agnostic with respect to unit commitment characteristics, so they do not factor unit commitment in their decisions, versus our proposed approach that I presented before that include the consideration of all these complex unit commitment characteristics. And this shows that through the proposed approach, the strategic profits are increased, and this gives a sign to regulators that they have to be aware of this potential as we move towards complex bidding mechanisms. So concluding this, some of the key messages: market power effects are both time dependent but also location dependent in case of network congestion. The ability to capture unit commitment characteristics can increase the potential of market power by strategic player, and this needs regulatory attention. And finally, that flexible demand and energy storage can overall reduce market power effects, and these benefits are location dependent in cases of network congestion. So by this, I will close this part and pass the floor back to Arne for concluding this session. Thank you.
Thank you, Dimitrios, and thank you to all the speakers, both for their contribution, obviously, to the original report and the presentation today. So flavors, as we said, for a lot of our research topics. And just to round out our presentation, I'm going to try and provide some of the common conclusions, the threads that run through all of the insights and results that we have discussed today and are discussed at length in the report itself. I think there's roughly 3 areas. First one being that what our results and our studies have really shown, and through specific cases and models, is that these innovative designs can facilitate renewable integration. So we see this common threads like a closer to real-time system service markets that on the one hand reduce the need for flexibility because there's better forecasts, there's better knowledge of networks, we have better information available, and also reduce the cost of flexibility. So this is both for allocating to conventional resources because we can schedule more precisely based on what they're already doing, but also allowing alternative resources to participate more. We have also decided that new technologies are key flexibility enablers and providers in the very obvious sense that they allow the use, the coordinated use of a bunch of distributed resources, but obviously also as providers. So we saw variable renewables, demand, response, and storage play their part in providing these new products. And then obviously also that coordination, both vertical and horizontal, is crucial. We saw on TSO level, this management of conflicts between more local and more national or even supranational optimization priorities that we get in the case of TSO coordination, where there we're talking reserve exchange and sharing, but also congestion management. Second part is that there are some specific design and implementation challenges that were identified and discussed, not always in detail here, but definitely in the report, when it comes to, for example, dealing with the more complex market operations. Markets will be more dynamic, there will be more types of participants and participants in general, and more integration of different services, which when we go to a cross-border integration, we see these challenges, and in addition, a bunch of challenges related to the harmonization of different products and different markets. There's also the obvious challenge of figuring out how to share costs and benefits, and we've tried to generate some insights into that in this report, again, vertical and horizontal, but for the operational level, but then on the investment level, some serious questions on shared assets when we're sharing reserve capacity, how this works, or investments that sometimes needs to happen in another control area to benefit a specific control area. There's the new potential market power effects that we just heard about, where demand response and storage can decrease market power effects, but under certain circumstances might increase them, and where definitely when we study these kinds of things, the technical constraints need to be taken into account to provide a clear picture. And finally, the provision of sufficiently stable investment signals and their importance to actually drive the investment in flexibility, in the capacity flexibility that we will need. And so challenges around delivering adequate remuneration and considering market situation in the smaller system service markets compared to the energy markets. Finally, I think the main takeaway here is that it is important to act sooner rather than later, because as we see across all reports and all research, the impacts of these kinds of things increase as the renewable share increases. So that I would say in the first step points to the fact that partial design improvements are worthwhile. We saw in some of the cases that as we're moving to real time, there's obvious benefits already from going from weekly to daily or hourly or quarterly, you know, depending on the application that would unlock more or less of the benefits. But also in terms of market integration, there are certain services that might be easier to integrate early on, and also cross-border in the case not discussed in detail here, but the exchange of reserves where we just exchange is easier than obviously when we go to a sharing stage and we also have to do a joint sizing exercise among TSOs. Final point to conclude on is that what is really important here, and this is true for other aspects of the power system, is that the midterm seems to be the key challenge. You know, long term, we could see reasonably sufficient signals coming from an energy market in terms of driving flexibility investment, for example, certain storage assets to already balance down a lot of wind and solar. But in the midterm, we have this challenge where there might be potentially insufficient returns leading up to it with an increasing flexibility need. So we might not have the means there when we need them. So that is a final challenge really to overcome. And with that, I think we conclude the content part of our presentation. I want to thank you all, as well as the speakers and the organizers again for attending, and we'll be very happy to take any questions you might have.
Thank you very much, Arne. So we only have a couple of minutes left, but as technical manager, I would like to thank as well all the speakers for very clear presentations of their research. There are many interesting and not so easy subjects to address. I don't want the attendants to be frustrated by only having a flavor of this research, but be aware again that the deliverable with the complete results will be available by the end of the month. It will be public. And as the recording of the webinar and the slides, it will be available on the project websites, as well as the previous webinars recording and slides. So 2 questions maybe that we had through the Q&A. So first question is a very short question to Gwen. It's a question about the tool that is used for the market simulator. If you could explain, please, what tool is used.
Well, it's an agent-based model, as I said, that consists of different blocks. Yeah, I don't know. Yeah, it's a very short, very open question. Yes, thanks, Hans-Peter. So we have the 3 blocks here, and then yeah, we built it into Python. And then we have different modules which each do their part. So for instance, there is a time series forecaster where we have included historical data on weather and on prices to help with the forecast for the day ahead market prices and reserve prices. There is another, well, then we have the techno-economic parameters, for instance, that we have included for the different technologies. Then the bidding strategies, the bid simulator, which takes all of these into account. Also the information blackboard where participants can find data from previous simulation cycles. Then we have this event calendar, which runs through the time sequence, which runs the different markets, the MFRR and the day ahead in the cycles that we include in the simulation. And then for the market operator, the market configuration, yeah, for the different markets, there we can include different product characteristics, different market clearing mechanisms, pay as bid versus pay as clear. Yeah, I don't know if that sufficiently answers your question. Otherwise, just feel free to send me an email and we can discuss it further.
Maybe just to ask if it's a public tool, it's a non-trivial tool. It's still research.
Yes,
yeah,
it's still research. It's not public yet.
Okay, thank you very much. Then we have a question that is more to Arne or Eric regarding joint and sequential procurement. So you have shown that there's an additional cost of sequential energy reserve markets compared to the joint day-ahead market clearing. So as shown in the webinar last week, it was stated that the optimization operator role could be played by the TSO for the coming reserve markets. How do you suggest to organize a joint day-ahead market clearing with optimization operator role played by TSO for reserve markets, while the optimization operator role is currently played by market operator in the like of IPEX? So it's a bit of an open question as well, but so
yes, I'll try. I guess I'll try and take the first stab at it, and Eric can always complement if I'm missing something. I think the main question here is about who collects the bids and then who runs them, and what kind of information does this operator need to be able to do so. And so this is where we might wonder, what kind of information do we want to be sharing with TSOs or market operators? I would say there's those are questions that need to be studied a little more in terms of, we studied this from a unit commitment model perspective. This is where we need to do some more research into what would market bids look like, what kind of information would be available for sharing, and also more specifically, which reserves will we prioritize for integration with the day-ahead energy market. I think MFRR is probably the more substantial one before we're going into other reserve and system service markets, and to be seen whether there we would actually go that far. So I think the first question would be to really establish what information would need to be shared, and then wonder whether the market or TSO operator is then the most appropriate for playing this joint role. So my sort of first answer, and again, also as Gwen said, we're also obviously willing to go in a little more detail in a further discussion through email or something. Eric, I don't know if you want to add anything to that.
Yeah, maybe quickly. I think what we aim to do is really quantify the two extremes and then use models to do that. I think given the system that we have in Europe, it's clearly different from, for instance, what we have in the US with an independent system operator. I think what the analysis we did, it shows the two extremes, but we also, for instance, show that the cost difference, so the additional cost of having a sequential market, that the difference also becomes smaller if you have new sorts of flexibilities coming into the picture, like flexible load, or if you also allow renewables to participate, if you set up the market in a sufficiently flexible way. So yeah, you should maybe not look at it like two extremes, saying, okay, it needs to be joined, but yeah, we do quantify, and we also show how we can come closer to that solution, for instance.
Thank you. And the last question on the Q&A that we will take now. So it's a question for CNR. So I don't know, Endika or Michal, regarding the PST study, have you checked the impacts on the inter-TSO compensation for the cross-border tariff in your study?
So, okay, so here Endika speaking. So as I understand the question, so it's related to if the congestion rents mechanisms that they have nowadays, they are, if we have compared those mechanisms with the current cost sharing. So if the question is like that, so I would say that those congestion rents, normally they reimburse the TSOs, those two TSOs that are responsible for the cross-border line. So it's some kind of market mechanism based on the old paradigm. But if today we change the paradigm into more coordinated way, that we could involve even all the third party, then the third party is not going to receive any congestion rent from that cross-border that is really far from that country. Yeah. So we didn't make any benchmarking with the current mechanisms, but I would say that is for the old paradigm. Yeah. I'm not sure if my colleagues would like to add something else. Yeah, but I would say that that's my impression.
Thank you very much. We need to close the session now. So thank you again very much. And please contact us if you have further questions or if you'd like to interact with our researchers. And you are welcome. You can see here on the last slides all our contacts for social media. So thank you very much. And I hope that you will join us again in further next webinars that will be coming up in the future. Thank you very much.